So this module is going to build on the second module where we focused on raster data. And in this case, we're going to be talking quite a bit about one specific type of raster data, and that's satellite imagery, and a little bit about how we can begin to analyze it and how it might be useful for different tasks in GIS. So this is all based on the electromagnetic spectrum, which we addressed in some of the earlier modules as well, where we have multiple different wavelengths of light, some visible, some not visible, that we can use to analyze certain types of land cover, and different satellite sources sample different ones of these. Now what's important to remember, and I'm just going to hit this again as a review, is that what we're dealing with here is reflectivity. So the color of an object is controlled by how much light it reflects in each wavelength. So some reflect certain wavelengths, some absorb certain wavelengths. So something that looks blue to us is actually reflecting blue light and absorbing everything else. And the same thing's true in other spectra as well. And when we're talking about satellite imagery, this is what they're usually measuring. This is what satellites are usually measuring. And this is all part of the concept of remote sensing. And in this case, a remote sensing is really just something that senses energy remotely. Whether it's actively doing this by sending out a signal and then seeing what comes back to it, something like radar or LiDAR, or whether it's doing it sort of passively, whether it's working off of light that's come from the sun and has bounced off the surface and then coming back to the sensor, something like a digital camera without a flash, or a lot of these satellite imagery sources. Now, other terms that I just want to make sure that are fresh, coming from previous modules, are the concepts of panchromatic and multispectral imagery, or panchromatic and multispectral images, where panchromatic is cross different colors, panchroma, essentially a black and white photograph sampling either all of the visible spectra of light or a little bit more, the reflectivity in those spectra. And a multispectral image is essentially multi-bands, like a color image, where we're sort of using little swaths to recreate color on the computer monitor. Now, in the specifics of satellite imagery, the nature of different satellite sources are usually defined by different types of resolution. So we talked about spatial resolution already, so the area on the ground represented by each pixel. But there's a few other types of resolution that are important for understanding satellite imagery as well. Things like temporal resolution, spectral resolution, radiometric resolution, each of which I'm going to go over in a little bit more detail. But then there are a few others that I'm not, things like view angle resolution that might control how many different angles the camera, the sensor on the satellite can look at. So spatial resolution we've already gone over. Essentially it's defined as the length in real-world coordinates of one side of each square pixel in the image. So a 10-meter resolution image would have 10 meters on the side of each pixel. It would be 100 square meters covered by each one. 5-meter would be 5 meters on each side, cover 25 square meters. This makes a lot of difference for how detailed the image might look, as you see here from examples of several different satellites and sort of what their resolution might be, ranging anywhere from 30 meter, 90 meter, down to 60 centimeters, so sub-meter resolution. When we're talking about temporal resolution, this is essentially the number of days between overhead passes at the same location. So we think about these satellites as orbiting the Earth. It's the number of days that it's going to take for that satellite to get back to going back over the exact same spot on the globe. These can be anywhere from 2 weeks, a month, down to some that circle very, very rapidly, that orbit very rapidly and might cover the same spot twice a day. Now that's not to say that every single satellite covers every point on the Earth systematically. Some of the orbital patterns don't really cross over the poles as well. Spectral resolution, in this case it's the number, spacing, and width of the sampled bands of wavelengths of light that we have. So when we're thinking about some of these sampling red, green, and blue, and then often the near infrared, it's essentially how many bands there are that are being sampled and what the width of them is. A higher resolution in this case would mean more precision in the representation of different spectral signatures. So if we wanted to figure out what the signature of a particular type of land cover is, whether it be forests or concrete or something like that, we would have more data available to be able to figure out what the specific signature of that would be. This is just an example of a few of these from the Landsat satellite, different wavelengths that are being sampled. There's 7 of them in this case. Radiometric resolution, in this case what we're talking about is the number of possible data values reported by the sensor. So when we talked in the earlier modules about 8-bit resolution, where we have 2 to the 8 values, 256 possible values, 0 to 255, that's a measure of the radiometric resolution of a sensor. That means there are 256 possible values that you could have. Some of them have 16-bit resolution, which have a little over 65,000 possible values. Some of them even have more than that. So it's a measure of how many different possible values there are in the image itself. The value that we then have for this, we usually call either the digital number or the brightness value. Now I want to turn to talking about some of the different imagery sources that we're going to work with, particularly the ones we're going to work with in the demo for this particular module. But before that, I want to just address the idea of ortho imagery as well. Ortho images are essentially true color images, so it's a photograph with any distortions caused by tilts in the camera or topography of the land that have been removed from them. So they've gone through the projection process, the georeferencing process, and a little bit beyond. Now these are really common that you'll see as the base layer for a lot of maps. This is what you see in Google Earth, and they usually come from either aerial photographs or satellites. And they're available for the entire country through the US GIS Earth Explorer, which I'll show the link to in a little while here. Now the first satellite I want to talk about is one of the more common ones for panchromatic imagery, and this is the SPOT satellite. It samples at, there's been a few different incarnations of it. The ones we're going to be working with in the demonstration are pre-1999, and they're freely available through the USGS. And these are panchromatic images at 10-meter resolution. So they're pretty high resolution to have for that time period. The newer SPOT satellites are all commercially available, and they sample at a higher spatial resolution, and usually two bands in the visible spectrum and then 2 in the near infrared. This is fairly common that they won't sample in the blue band because there's not a whole lot in nature that's blue but not green. So it's usually, if they're going to skip one in the visible spectrum, it's usually the blue band. So this is what a SPOT image looks like. You can see that it is panchromatic and it is relatively high resolution. Now the next satellite I want to talk about is the Landsat satellite. This is the longest running Earth observing satellite. It's a US project. And it's actually been a series of now 8 different satellites with different sensors that are pretty similar between them. It orbits about every 16 days. And almost all Landsat data is freely available for academic uses through the USGS. So it's a really, really powerful satellite, both because it's been around since the early 1970s, sampling in a pretty systematic way, but also because it's all available pretty freely. So there are 2 main sensors that the Landsat has used. The early one is the multispectral sensor, the Landsat MSS, and it's sampled at a 90-meter resolution, 4 different bands, 2 in the visible spectrum, 2 in the near infrared. And then the more common one that we see today is the Landsat TM and ETM sensor. They're very similar. The only real difference is the ETM added a panchromatic sensor at a 15-meter resolution, whereas all the other multispectral bands are at 30-meter resolution. It samples red, green, blue in the visible spectrum, 3 in the near infrared, and 1 in the thermal infrared. So this is an older Landsat image. This is from the MSS sensor. You can see that it still shows us that very distinct color pattern that we associate with vegetation in satellite imagery. Because it doesn't have all 3 visible light bands, it's kind of hard to recreate true color easily with it, but we can do it with some post-processing techniques. And then the more recent Landsat is a higher spatial resolution, and we can show it as true color as well if we want to. Now, one of the neat things about Landsat imagery is something called the Global Land Survey. And these are standardized, treated Landsat imagery for the entire globe at 5 different times throughout the tenure of the Landsat satellite. Now, why is this important to have a treated and standardized surface like this? Well, the Landsat satellites go along little swaths, so you have time period, you have different days that might be right next to each other, images from different days. And because a lot of the because all of these imagery are measuring reflectivity, percent of light being reflected back in certain bands, it can change based on whether there's lights on, whether it's at night, all sorts of different reasons. So or whether there's cloud cover. So it's important that they're then standardized, so they might be relatively the same, but now they're absolutely the same as well. So they match up better that way. And if you're going to do anything at a continental or even a state level, it's important to try to use these standardized ones. Now, another satellite that we're going to work with is the ASTER satellite. This is the Advanced Spaceborne Thermal Emission and Reflection Radiometer. And this is a project that's been around since 1999 as a joint US-Japanese project. The ASTER satellite has a very high spectral resolution. It samples 14 different bands, both in the near-infrared, shortwave infrared, and thermal infrared, and in addition to visible light as well. We can see here that it doesn't sample in blue, so we have 2 bands in visible spectrum and then 2 in the near-infrared. And one other kind of neat thing about Landsat is there's actually 2 band 3s. There's a sensor facing straight down and one facing off to the back. And what this allows the satellite to do is create a measure of topography as well. It can use those 2 sensors that have different view angles to recreate topography. And we'll talk about that a little bit more in a later module. So these are just a few examples of what ASTER imagery might look like. It does have a higher spatial resolution as well, 15 meters. So it is a very useful complement to some of the other satellite data sources. Now, there are a few others that we're not going to work with directly in the demonstration, but I think are probably useful to know about. The MODIS satellite is one of these. It's a medium resolution, about 250 meters up to 1 kilometer resolution. But it does have 36 spectral bands that it samples. So it actually gives you quite a lot of data on a larger scale in many, many different wavelengths of light. The AVHRR is the Advanced Very High Resolution Radiometer. This is a 1 kilometer resolution image or satellite that orbits very, very rapidly, twice daily, and is very useful for like broad scale weather patterns and things like that. We also have a few others, things like declassified spy satellites. There's been a few processes of declassifying these, which have extremely high spatial resolution usually, but they're entirely panchromatic and they have relatively limited coverage for the time periods that they were being used. And then there are also the modern commercial satellites as well, things like QuickBird and Digital Globe, which are the base maps for Google Earth and Google Maps. And these have a very, very high spectral or spatial resolution, 1.6 meters multispectral and about 60 centimeters panchromatic. So there really are a lot of these commercially available sources as well. Just going to show a few examples of what these look like. This is MODIS data. See, it's good on a country or continental scale. The AVHRR gives us very good measures of things like this hurricane. And then our commercial data and declassified data as well. Now, one thing I just want to stress here is that there are a lot of companies out there that will offer commercial processing and download of a lot of these satellite imagery sources. Almost all of the imagery we've discussed here, unless I've distinctly said commercial, is freely available for academic purposes. So the notable exception is those commercial QuickBird satellites and things like that, and some of the spot imagery. And this USGS Earth Explorer is a very useful tool for finding imagery and being able to download it with registration. So I encourage you to explore there and find if there's any of these data sources that might be useful for any projects that you have. Now I want to talk a little bit about some of the uses of satellite imagery as well, particularly the ones that we're going to focus on in the demonstration for this module. Now the first of these is what we call a vegetation index. In the earlier modules, we've talked about how that near-infrared band of light is very, very good at distinguishing vegetation. And a vegetation index is a way of standardizing this into a synthetic image layer that sort of gives us an idea of the strength or the health and density of any vegetation. So it's a new layer that provides a kind of a unique information not necessarily found in the individual bands. And this is usually done by looking at the relationship, the the relationship between the near reflectivity in the near infrared and the reflectivity in the red band. And that's because things that are reflecting very strongly in the near infrared but not very strongly in the red are probably vegetation and healthy vegetation. Things that are reflecting very strongly in both or about the same in both are probably something else. So there's several different vegetation indices that we can use. Most are kind of functionally equivalent and use some combination of red and near infrared. But the most common one and the one we're going to focus on is something called the NDVI, or Normalized Difference Vegetation Index. And it's essentially a scaled version of the relationship between those two bands where the values are ranging from -1 to 1. So well-vegetated areas are going to have significantly higher near-infrared, so it's going to end up in a value that's closer to 1. Things that are about the same between them are going to end up closer to 0 or possibly slightly negative values. Things like water or rocky, dry, sparse vegetation are going to have much lower values because their reflectivity in the red and near-infrared are about equal. So this is an example of one of these. I should point out here that the program we're going to be using for this, ArcGIS, gives us the measurements in a slightly different way. Instead of being scaled from -1 to 1, they're scaled from 0 to 200. The data are exactly the same. Just anything below 100 is usually not particularly vegetated. Anything above 100 is getting increasingly dense in vegetation. So the colors that we're seeing here are things that are red are 0 or lower, 100 or lower. And these are things like the city of South Bend, the urban areas, any places where there's just simply not much vegetation. Crop fields and forests tend to be somewhere in between, the lighter and the darker greens. And there are probably a few little spots in there that are blue. That would be very, very dense water. The river doesn't necessarily show up just simply because it's relatively shallow, so there's some reflectivity coming off the bottom as well. Now we can find similar sorts of indices for various geological measures as well, because different minerals reflect differently in some of the higher wavelengths of light as well. And this is going to depend a lot on the satellite and the data that you have. These have been kind of standardized for Landsat, so there are a few different indices that we could calculate here. We could look at, say, iron oxides or clay minerals or other types of iron minerals based on looking at the combinations of different bands. Now the last thing that we can also do is something that's called a resolution merge or pan sharpening. And this is essentially taking a high spatial resolution panchromatic image and using it to artificially sharpen a lower resolution multispectral image. So if you think about the fact that that panchromatic image covers all of the visible spectrum and sometimes into the near infrared, it's got the overall reflectivity in there. That can be used to artificially increase the resolution of the other image of the panchromatic or the multispectral image. Now this really only works if they're from about the same time or exactly the same time. A lot of the satellites will have a panchromatic band that can be used to artificially sharpen the multispectral data that comes from it. So this is a really pretty common task, and it's something that we're going to work with a little bit here. So that's a review of the different sources of satellite imagery, when you might want to use some of the different ones, what some of the different satellites are good for, and some of the different techniques that we can use. In the following module, we're going to focus a little bit more on creating vector data and when we might want to use some of these processes to actually digitize parts of maps or parts of satellite data.